What happens when you get to a really, really big number like this one? What does this number mean? Can we translate this to a regular number that we're used to? Let's consider the numbering system we're used to. What does 3,452 really mean when you break it down? This first column is known as the ones column. You probably remember this from early on in learning to count. The 2 there means there's 2 in the ones column. This next column is the tens column. Why is that the tens column? Because when we get to 10 is the first time we use that column. Likewise, the third column is the 100s column, because the first time you use that column is when you get to 100. Each number in this column represents 100. The last column is the thousands column. How do we know what this number is, or how do we get to this number? We have 2 ones, 5 tens, 4 100s, and 3 1000s. When you add all those up, you get the same number, 3,452. Well, binary is actually very similar. In the first column is still your ones column. That hasn't changed. The second column, you get to that column or you roll to that column when you're at 2. That means this is the 2's column in binary. The third column, you get there when you get to 4. This is the 4's column. Now you'll notice, just like we said at the beginning, how many states you can represent. With each wire or with each new column, you're doubling the amount of numbers that you can represent. So each column is twice as much as the last one. This is said to be based on the number 2. This numbering system or binary system is also known as base 2. After the 4's column, the next column represents 8, or said another way, 2 to the third power. Double it again, you get to 16. The next column is represented by 32, 64, 128, and so on. Each column, it represents twice what the last column represented. Just like in the regular number system, each column represents 10 times the number of the last column. Our numbering system that we use is called base 10. It's based on the number 10. Each column is 10 times greater in value than the previous column. In binary, because there's only 2 states, it's said to be based on the number 2, and each column is 2 times larger than the previous column. Let's use this same technique as we used to figure out what 3,542 was earlier to figure out what this big number is. In the first column, we have 1, 1. In the second column, we have 1, 2. Right? Just like in 3,452, for the second column, we had 5 tens. Well, we only have one of the 2 columns, so we write it down. In the third column, we have 1, 4. The fourth column represents 8, but we don't have any 8s, so we skip that column. The fifth column is a 16, 32, 64, 128, 256, and then we don't worry about the next 2 columns. Then 2048, 4096, 16384, 32768, 65536, 262,144, and finally 2,097,152. If we add all those up, we get 2,480,631. This big number at the top is actually 2,480,631. If you don't believe me, pause the lecture, pull out the calculator on Windows, type in 2,480,631, switch it to programmer mode, and look at the bin or binary number at the bottom. You'll notice, if you take time, that this is the number we have typed at the top. We'll explain hex and octal next, but let's just realize that we've represented a really large number, a number in the 2 millions, with just a few wires. That's a lot of different numbers we can represent with just a few wires. Each time we add a new wire, we double the amount of numbers that we can represent.